The story of the universe and Earth's formation spans billions of years. It is a journey that begins with the birth of the universe itself and traces the formation of stars, galaxies, and eventually our home planet. Understanding this journey not only provides insight into the natural history of our planet but also into the origins of life and the interconnectedness of all things. This narrative helps us reflect on our place in the vastness of the cosmos. Let's start with Big Bang Theory. The Big Bang Theory is the prevailing cosmological model for the universe's origin and subsequent evolution. It posits that the universe began as an extremely hot, dense state and has been expanding and cooling ever since. While the exact details of the very first moments are still a subject of ongoing research, the theory provides a framework for understanding the universe's history. The Big Bang Theory suggests that approximately 13.8 billion years ago, the universe was incredibly small, hot, and dense, existing as a singularity, a point of infinite density and temperature. This singularity, for reasons still unknown to science, began to expand rapidly in a process known as inflation. During this period, the universe grew exponentially in size, stretching space itself and cooling dramatically. Following inflation, the universe continued to expand, but at a slower rate. As it expanded and cooled, fundamental forces began to emerge. Gravity, the weakest but longest reaching of these forces, separated from the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. This period, known as the electroweak epoch, lasted for a fleeting moment, followed by the separation of the electromagnetic and weak forces. As the universe continued to cool, subatomic particles began to form. Quarks, the building blocks of protons and neutrons, emerged from the energy of the expanding universe. These quarks then combined to form protons and neutrons, the constituents of atomic nuclei. This period, known as nucleosynthesis, saw the formation of the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. The universe continued to expand and cool for hundreds of thousands of years. During this time, the energy of the universe gradually decreased, allowing protons and electrons to combine and form neutral atoms. This process, called recombination, led to a significant drop in the interaction of matter with light, allowing light to travel freely through the universe. This cosmic microwave background radiation, a faint afterglow of the Big Bang, can still be observed today and provides crucial E. Following recombination, the universe entered a period known as the Dark Ages, characterized by a lack of bright, luminous objects. Gravity began to pull matter together, forming clouds of gas and dust. These clouds gradually collapsed under their own gravity, leading to the formation of the first stars. The intense heat and pressure within these stars ignited nuclear fusion, releasing vast amounts of energy and synthesizing heavier elements. The light from these first stars ionized the surrounding hydrogen gas, creating a period known as reionization. This reionized gas filled the intergalactic space, making the universe more transparent to ultraviolet radiation. Over time, these first stars and galaxies merged and evolved, forming the complex structures we observe today, including galaxies, galaxy clusters, and superclusters. The Big Bang Theory continues to be refined and expanded upon through ongoing research and observations. Scientists are constantly seeking to understand the earliest moments of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. While many questions remain unanswered, the Big Bang Theory provides a robust framework for understanding the universe's origin and evolution, and continues to inspire and wonder in the minds of scientists and the general public. It is important to note that the Big Bang Theory describes the evolution of the universe from a very hot and dense state, but it does not explain the origin of this initial state. The question of what existed before the Big Bang remains a subject of ongoing debate and speculation. Some scientists propose that our universe may be just one of many in a multiverse, while others suggest that the Big Bang may be part of a cyclical process of expansion and contraction. Despite these unanswered questions, the Big Bang Theory remains the most widely accepted and scientifically supported model for the origin and evolution of the universe. It provides a powerful framework for understanding the cosmos and continues to drive scientific inquiry into the fundamental nature of reality. As technology advances and our understanding of the universe deepens, we can expect to gain even greater insights into the mysteries of the Big Bang and the vast expanse of the cosmos. Do you know how stars were formed?
Alright, let me explain you how stars were formed. The vast universe we observe today, teeming with stars, galaxies, and cosmic wonders, began its journey long ago as a consequence of the Big Bang. As the universe expanded and cooled, the dance of gravity began to shape its destiny. Regions within the expanding cosmos, initially quite uniform, experienced slight density fluctuations. These subtle variations, like ripples in a pond, became the seeds for the cosmic structures we witness today. Gravity, ever present and relentless, pulled on these denser regions, drawing together vast clouds of gas and dust. These cosmic clouds, composed primarily of hydrogen and helium, the primordial elements forged in the fiery aftermath of the Big Bang, began to collapse under their own weight. As these clouds contracted, their cores grew hotter and denser. This increasing pressure and temperature ignited a thermonuclear furnace at the heart of these collapsing clouds, marking the birth of a star. These first stars were behemoths, far more massive than our Sun. Their immense size and scorching temperatures fueled furious nuclear fusion reactions, converting hydrogen into helium and releasing immense amounts of energy. However, their very brilliance proved to be their downfall. These massive stars lived fast and died young, burning through their fuel reserves at a prodigious rate. When their nuclear fuel was emptied, these stellar met their demise in cataclysmic explosions known as supernova. These supernovae were not mere fireworks displays, they were cosmic alchemists. The intense heat and pressure within the exploding star forged heavier elements, such as carbon, oxygen, iron, and even gold, from the lighter elements at its core. These newly created elements, scattered across the cosmos by the supernova's blast wave, became the building blocks for future generations of stars, planets, and even life itself. As more and more stars ignited, they began to congregate, drawn together by mutual gravitational attraction. These stellar gatherings, initially loose and diffuse, gradually coalesced into larger structures, forming the first galaxies. Our own Milky Way galaxy, a vast swirling disk of stars and gas, is a testament to this process of galactic assembly. The early universe was a dynamic and chaotic place. Galaxies collided and merged, their shapes and structures distorted by the gravitational dance. Some galaxies, through a series of mergers and acquisitions, grew into colossal elliptical galaxies, while others retained their swirling disk shape, like our Milky Way. These interactions, while violent, played a crucial role in the evolution of galaxies, enriching them with new stars, gas, and dust. Over billions of years, galaxies continued to evolve, their shapes and sizes influenced by a myriad of factors, including the rate of star formation, the presence of supermassive black holes at their cores, and interactions with neighboring galaxies. The universe, once a relatively uniform expanse, became a tapestry of diverse and intricate structures, a testament to the power of gravity and the relentless march of cosmic time. The story of star and galaxy formation is a tale of cosmic evolution, a journey from the primordial chaos of the early universe to the intricate tapestry of galaxies that we observe today. It is a story of creation and destruction, of birth and death, a cosmic symphony played out on the grandest of stages. And within this vast cosmic tapestry, within one ordinary galaxy among billions, lies our own solar system, a testament to the enduring power of creation and the delicate balance. After all, this solar system was formed. The birth of our solar system, a captivating cosmic drama, unfolded over eons, beginning roughly 4.6 billion years ago within the vast expanse of the Milky Way galaxy. The stage was set within a colossal molecular cloud, a diffuse region of interstellar gas and dust, primarily composed of hydrogen and helium, the primordial elements forged in the fiery furnace of the Big Bang. Within this immense cloud, gravity, the ever-present cosmic force, exerted its influence. Subtle density variations, perhaps triggered by the shockwave of a nearby supernova, caused certain regions within the cloud to become slightly denser than others. These denser pockets, like cosmic eddies, began to attract more and more matter through gravity, gradually increasing in mass and density. As this gravitational collapse intensified, the cloud began to spin faster, a consequence of the conservation of angular momentum, much like a figure skater spinning faster as they pull their arms closer to their body. This spinning cloud, now a swirling vortex of gas and dust, flattened into a disk-like structure, a protoplanetary disk, with a dense core at its center. This core, under the relentless pressure of its own immense gravity, reached temperatures that ignited nuclear fusion, the process that transforms hydrogen into helium, releasing vast amounts of energy. Thus, our Sun was born, a fiery beacon at the heart of the nascent solar system. The remaining material within the protoplanetary disk, a swirling maelstrom of gas, dust, and ice, continued to evolve. Tiny dust grains, colliding and sticking together through a process known as accretion, gradually grew into larger and larger objects, much like a snowball rolling down a hill. These growing bodies, known as planetesimals, ranged in size from pebbles to objects the size of small moons. The conditions within the protoplanetary disk varied significantly with distance from the nascent Sun. In the inner regions, closer to the blazing young star, temperatures were high, vaporizing ice and leaving behind only rocky materials. These rocky planetesimals collided and merged, eventually forming the terrestrial planets, Mercury, Venus, Earth, and Mars, small, dense worlds composed primarily of rock and metal. The conditions within the protoplanetary disk varied significantly with distance from the nascent Sun. In the inner regions, closer to the blazing young star, temperatures were high, vaporizing ice and leaving behind only rocky materials. These rocky planetesimals collided and merged, eventually forming the terrestrial planets, Mercury, Venus, Earth, and Mars, small, dense worlds composed primarily of rock and metal. The formation of Earth was a particularly dramatic and eventful episode in this cosmic saga. While accreting from the protoplanetary disk, a catastrophic collision occurred, involving a Mars-sized object that impacted the young Earth. This colossal impact, a truly titanic event, had profound consequences. The debris ejected from this collision coalesced to form our Moon, a unique and enigmatic satellite that has played a pivotal role in the evolution of life on Earth. The early Earth was a chaotic and dynamic place. Intense volcanic activity released vast amounts of gases, forming a primordial atmosphere, while the relentless bombardment of asteroids and comets continued to shape the young planet. Over millions of years, the Earth gradually cooled, forming a solid crust. The impact of icy comets delivered water, eventually filling the basins of the early Earth to form the vast oceans that cover much of the planet's surface today. The formation of the solar system was a complex process, a cosmic dance of gravity, accretion, and violent collisions. From the collapse of a molecular cloud to the birth of a star and the formation of planets, moons, and other celestial bodies, the solar system's history is a testament to the dynamic and ever-changing nature of the universe. It is a story that continues to unfold, with ongoing interactions between planets, moons, and other objects shaping the future of our cosmic neighborhood. Now, we shall talk about the early Earth formation. The early Earth was a far cry from the serene blue marble we know today. Imagine a world of molten rock, where volcanoes erupted with furious intensity, spewing lava and ash into the sky. This was a time of relentless bombardment, as asteroids and comets, remnants of the solar system's formation, rained down upon the young planet, leaving craters scarring its surface. The atmosphere, thick and noxious, was a far cry from the oxygen-rich air we breathe, composed primarily of carbon dioxide, nitrogen, and water vapor. Life as we know it would have been utterly impossible in this harsh, inhospitable environment. Yet, within this crucible of chaos, the foundations for life on Earth were being laid. The intense heat generated by the planet's formation caused the Earth to differentiate, a process akin to the separation of oil and water. Denser materials, such as iron and nickel, sank towards the planet's core, while lighter elements, like silicon and oxygen, rose to the surface, forming the Earth's crust and mantle. This internal churning, driven by the immense heat trapped within the planet, released vast amounts of energy, fueling volcanic eruptions and shaping the planet's surface. One of the most crucial consequences of this internal differentiation was the formation of the Earth's magnetic field. As molten iron in the outer core swirled and churned, it generated a powerful electric current, creating a magnetic field that envelopes the planet. This magnetic field acts as an invisible shield, deflecting the harmful solar wind, a stream of charged particles emanating from the sun. Without this protective shield, the solar wind would strip away the Earth's atmosphere, leaving the planet vulnerable to the harsh radiation of space. As the planet gradually cooled, the surface began to solidify, forming a thin, brittle crust. Volcanic eruptions continued to release vast amounts of water vapor into the atmosphere, which eventually condensed and fell as rain, accumulating in vast basins to form the first oceans. These primordial oceans, vast and deep, played a critical role in shaping the course of Earth's history. They absorbed heat from the sun, moderating the planet's temperature and preventing extreme fluctuations. More importantly, the oceans provided a unique environment for chemical reactions to occur. The energy from volcanic eruptions, combined with the abundant water, provided the necessary conditions for the formation of simple organic molecules, the building blocks of life. These early molecules, including amino acids, the building blocks of proteins, and nucleic acids, the carriers of genetic information, may have formed in various locations, such as deep-sea hydrothermal vents, where hot, mineral-rich water emerges from the ocean floor, or in shallow pools of water exposed to the sun's energy. The early Earth, despite its harsh and chaotic beginnings, possessed the inherent potential for life. The relentless forces of nature, the volcanic eruptions, the asteroid impacts, and the slow, gradual cooling of the planet, all played a crucial role in creating the conditions that ultimately gave rise to the diverse and wondrous tapestry of life that now inhabits our planet. It is a testament to the resilience of nature and the remarkable capacity of life to find a foothold and flourish in even the most challenging of environments. The Archean Eon, a period spanning from roughly 4 billion to 2.5 billion years ago, marks a pivotal chapter in Earth's history, the emergence of life. This was a time of immense geological activity, with volcanic eruptions shaping the planet's surface and the slow cooling of the Earth allowing the formation of a solid crust in vast oceans. Within this dynamic environment, the first whispers of life began to stir. The earliest life forms were incredibly simple, microscopic organisms, vastly different from any life we encounter today. These were single-celled prokaryotes, lacking the complex internal structures of more advanced organisms. They were likely extremophiles, thriving in environments that would be inhospitable to most modern life, deep-sea hydrothermal vents, where scorching hot water gushes from the ocean floor, or perhaps even within the porous rocks beneath the Earth's surface. These primordial organisms likely obtained energy through chemosynthesis, a process where they extracted energy from inorganic chemicals in their environment, much like certain bacteria living in deep-sea vents today. This metabolic pathway, while seemingly simple, represents a remarkable feat of biochemical ingenuity, allowing these early life forms to survive and thrive in the harsh conditions of the early Earth. A major turning point in the history of life occurred with the evolution of photosynthesis, a revolutionary process that harnesses the energy of sunlight to convert carbon dioxide and water into organic matter. Cyanobacteria, often referred to as blue-green algae, were among the earliest organisms to develop this remarkable ability. Photosynthesis not only provided a new source of energy for life but also had a profound and far-reaching impact on the Earth's environment. As cyanobacteria flourished, they released oxygen as a byproduct of photosynthesis. Initially, this oxygen reacted with dissolved iron in the oceans, forming vast deposits of iron oxide, a process that led to the formation of banded iron formations, which are still visible in rocks today. However, over millions of years, the oceans became saturated with iron, and oxygen began to accumulate in the atmosphere. This gradual increase in atmospheric oxygen, known as the Great Oxidation Event, had a profound and transformative effect on the planet. It created a toxic environment for many of the early, oxygen-intolerant organisms, while paving the way for the evolution of more complex life forms that could utilize oxygen for respiration. The rise of oxygen in the atmosphere also led to the formation of the ozone layer, which shields the Earth from harmful ultraviolet radiation, further enabling the diversification of life on the planet's surface. The Archean Eon represents a crucial period in the history of life on Earth. From the emergence of the first simple life forms to the rise of oxygen and the transformation of the planet's atmosphere, this era laid the foundation for the incredible diversity of life that exists today. The story of life on Earth is a long and winding journey, and the Archean Eon, with its pioneering life forms and metabolic pathways, serves as a testament to the remarkable resilience and ingenuity of life. Same as Archean Eon, we have Proterozoic Eon. The Proterozoic Eon, spanning from 2.5 billion to 541 million years ago, was a pivotal period in Earth's history marked by significant changes in atmospheric composition and the emergence of complex life forms. One of the most profound events during this era was the Great Oxidation Event, which began around 2.4 billion years ago. This dramatic increase in atmospheric oxygen was primarily due to the activity of photosynthetic organisms, such as cyanobacteria, which released oxygen as a byproduct of photosynthesis. The rise of oxygen had a profound impact on the planet, transforming the atmosphere and paving the way for the evolution of more complex life.
The availability of oxygen led to the evolution of eukaryotic cells, a major breakthrough in the history of life. Eukaryotic cells are characterized by the presence of a nucleus, a membrane-bound organelle that houses the cell's genetic material. This complex cellular organization allowed for greater specialization and efficiency, enabling the evolution of multicellular organisms. Around 1.2 billion years ago, the first multicellular organisms began to appear. These early life forms were relatively simple, often consisting of colonies of cells that worked together. However, they represented a crucial step towards the development of more complex life forms, such as animals and plants. By the end of the Proterozoic Eon, more complex multicellular organisms had emerged. The Ediacaran biota, a diverse assemblage of soft-bodied organisms, flourished in the oceans during this time. These creatures, which included jellyfish-like organisms and frond-shaped life forms, represent a major step towards the diversity of life we see today. The Proterozoic Eon was a time of significant change and innovation, laying the groundwork for the subsequent explosion of life in the Phanerozoic Eon. The rise of oxygen, the evolution of eukaryotic cells, and the emergence of multicellular organisms all contributed to the remarkable diversity of life that exists on Earth today. The Phanerozoic Eon, a period spanning from approximately 541 million years ago to the present, represents a dramatic chapter in Earth's history, characterized by a breathtaking explosion of life and an ongoing saga of evolution and diversification. This eon, a term derived from the Greek words phaneros, visible, and zoikos, life, is aptly named, as it marks the period when life became abundantly visible and diverse across the planet. The Phanerozoic is further divided into three distinct eras: the Paleozoic era, Old Life, the Mesozoic era, Middle Life, and the Cenozoic era, New Life, each marked by significant geological and biological events that shaped the trajectory of life on Earth. The Paleozoic era, spanning from 541 to 252 million years ago, witnessed a truly remarkable event, the Cambrian explosion. This period saw an astonishing burst of evolutionary innovation, with the rapid diversification of animal life. Prior to the Cambrian, life was primarily confined to the oceans and consisted largely of simple, single-celled organisms. However, during the Cambrian, a dazzling array of new life forms emerged, including the ancestors of most major animal groups living today. The oceans teemed with bizarre and wonderful creatures. Trilobites, with their segmented bodies and intricate exoskeletons, dominated the seafloor. Cephalopods, such as the nautilus, evolved complex shells and became formidable predators. Jawless fish emerged, followed by more advanced fish with jaws, marking a significant milestone in vertebrate evolution. Life also began to venture onto land during the Paleozoic. Plants were the first to colonize terrestrial environments, followed by animals such as arthropods, including insects and spiders. Amphibians, the first vertebrates to venture onto land, evolved from fish, marking a crucial step in the conquest of terrestrial habitats. However, the Paleozoic era came to a dramatic and devastating end with the Permian-Triassic extinction event, the most severe mass extinction in Earth's history. Volcanic eruptions, climate change, and potentially other factors combined to create a catastrophic environmental collapse, wiping out an estimated 90% of marine species and 70% of terrestrial vertebrate species. This mass extinction event profoundly reshaped the course of life on Earth, clearing the way for the rise of new dominant groups. The Mesozoic era, spanning from 252 to 66 million years ago, is often referred to as the Age of Reptiles. Following the Permian-Triassic extinction, reptiles diversified and became the dominant land animals. Dinosaurs, with their diverse array of shapes and sizes, roamed the continents, while flying reptiles, such as pterosaurs, took to the skies. The Mesozoic era also witnessed the rise of flowering plants, a significant evolutionary innovation that transformed terrestrial ecosystems. Flowering plants, with their diverse array of colors, shapes, and scents, co-evolved with pollinators such as insects and birds, creating a complex and intricate web of life. However, the Mesozoic era also ended abruptly with a catastrophic event, the Cretaceous-Paleogene extinction event. This mass extinction, triggered by the impact of a large asteroid, led to the demise of the dinosaurs and many other species, including marine reptiles and flying reptiles. The Cenozoic era, which began 66 million years ago and continues to the present day, is often referred to as the Age of Mammals. Following the extinction of the dinosaurs, mammals, which had been relatively small and inconspicuous during the Mesozoic, underwent a remarkable adaptive radiation, diversifying into a wide range of forms and filling the ecological niches vacated by the dinosaurs. The Cenozoic era also witnessed the rise of grasslands, vast expanses of land dominated by grasses. This shift in vegetation led to the evolution of large grazing herbivores, such as horses, elephants, and deer, as well as the predators that hunted them, such as cats and dogs, around 2 million years ago.
The first members of the genus Homo appeared on the African savanna.
These early humans, with their increasing brain size and the development of tool use, gradually evolved into our own species, Homo sapiens, which emerged around 200,000 years ago. The rise of Homo sapiens has had a profound and transformative impact on the planet. Through agriculture, technology, and industry, humans have reshaped the Earth's landscape, altered the climate, and driven many species to extinction. The future of life on Earth now rests largely in the hands of humanity, as we grapple with the challenges of environmental change and strive to ensure a sustainable future for ourselves and all other living beings. The Phanerozoic Eon, with its dramatic bursts of evolutionary innovation, its periods of profound change, and its occasional catastrophic events, provides a captivating glimpse into the dynamic and ever-evolving history of life on Earth. It is a story of resilience, adaptation, and the remarkable capacity of life to thrive and diversify in the face of immense challenges.
We have Earth at this point. Earth today is a dynamic and vibrant planet, a testament to billions of years of cosmic evolution.
It teems with life, from the microscopic bacteria thriving in the deepest ocean trenches to the majestic giants roaming the savannas. A delicate balance of forces shapes our world: the relentless pull of gravity, the slow but inexorable movement of tectonic plates, and the continuous cycling of water through the atmosphere, oceans, and land. These natural processes, operating over vast timescales, have sculpted the Earth's surface, creating mountains, carving canyons, and shaping the contours of continents. However, the human impact on Earth is undeniable and profound.
Since the dawn of the Industrial Revolution, human activities have dramatically altered the planet's environment.
The burning of fossil fuels has released vast amounts of greenhouse gases into the atmosphere, trapping heat and driving global warming. Deforestation has led to the loss of vital ecosystems, while pollution has contaminated air, water, and soil, threatening the health of both humans and wildlife. The consequences of these human-induced changes are already becoming apparent. Rising global temperatures are melting glaciers and ice caps, leading to rising sea levels and coastal erosion. Extreme weather events, such as heat waves, droughts, and floods, are becoming more frequent and intense. The delicate balance of Earth's ecosystems is being disrupted, leading to biodiversity loss and the decline of many species.
Addressing these challenges is crucial for the long-term sustainability of life on Earth.
Transitioning to renewable energy sources, reducing greenhouse gas emissions, protecting biodiversity, and promoting sustainable practices are critical steps towards mitigating the impacts of human activity. Looking further into the future, Earth faces even more profound changes, driven by the inevitable evolution of our Sun.
Over the next billion years, the Sun will gradually increase in brightness, slowly but steadily warming the Earth. This gradual warming will eventually make the planet too hot to sustain life as we know it.
Oceans will evaporate, and the surface will become a scorching desert. In about 5 billion years, the Sun will exhaust its core hydrogen fuel and begin to evolve into a red giant. This phase will see the Sun expand dramatically, potentially engulfing Mercury, Venus, and even Earth itself. While the exact fate of Earth during this phase remains uncertain, it is likely to be engulfed by the Sun's expanding outer layers,
ultimately meeting a fiery demise.
These long-term predictions serve as a reminder of the impermanence of our world.
The Earth, despite its current vibrancy, is a temporary oasis in the vastness of space.
The story of the universe and Earth highlights the intricate connections between cosmic events and the evolution of life. It underscores the uniqueness of our planet and the profound responsibility we have to protect it for future generations. As we navigate the challenges of the present, we must also look towards the future, exploring the possibility of space exploration and the search for other habitable planets. These endeavors are not just about scientific discovery, they are about ensuring the long-term survival of humanity and the continuation of life beyond our own fragile blue planet. The future of Earth, and perhaps the future of humanity itself, may lie among the stars.